And for all the participants to know, the form link, sorry, was just updated, so you can go there and enter your emails. So let's get started.
Hello everyone, my name is Julian Mateshika and I'm passionate about robotics, open source and wearable devices. For the past 3 years I have been working with Natix at Fitbit as a firmware engineer. During this period I have touched various areas of the Natix operating system, device drivers, IPC mechanisms, loadable apps, but in my team I am mostly known as the file system guy because of my large contribution to Natix's file system SmartFS, about which I would like to talk a little bit in the following minutes. During these years, I have implemented few mechanisms such as file system check, bad blocks management, partial mapping, logical defragmentation, and sector cache. Before diving into each one of these subjects, I would like to discuss about the reasons behind these changes and why they were needed. At Fitbit, we build fitness trackers which have multiple hardware constraints, the most important being small RAM and ROM memories and small batteries. A full battery should last for at least 7 days. We have reduced SmartFS's RAM usage with partial mapping and sector cache. User data integrity and device reliability are top priorities for Fitbit. To accommodate these needs, we have implemented two mechanisms: file system check and bad blocks management. Having this said, it's time to move on to what is SmartFS and how does it work. I'm sure that not all of you are familiar with upstream SmartFS. Therefore, before discussing about the changes we have made at Fitbit, I want to introduce you to SmartFS. SmartFS stands for Sector Mapped Allocation for Really Tiny Flashes, and it has been designed around NOR flash memories. It has built-in warp leveling, which was obtained by having a separation between logical sectors and physical sectors with a one-to-one mapping between them. It has two layers, the one on top being called simply SmartFS, the blue one in the diagram. It only knows about logical sectors and it's responsible for managing files and directories. It communicates with the layer below, called SmartMTD, the yellow one, through a series of read, write, allocate, free logical sector operations. The middle layer, SmartMTD, is responsible for managing physical and logical sectors, perform wear leveling, and detect bad blocks. A block is bad if it has been worn out and it's not capable to store data anymore. At the bottom is the MTD flash layer, which responds to the middle layer's request of read-write page or erase block. Files and directories are managed by the top layer, SmartFS, and they are simply implemented as a linked list of logical sectors. Each sector has a header which stores its logical sector number and the next logical sector number. Let's take for example the file a.txt from the diagram. It has three sectors, 300, 400 and 500. These are logical sectors. Let's assume that in the current configuration each sector has 1 kilobyte. The other file b.txt has only two sectors. Both of these files are part of the data directory, the green one. A directory is also a linked list of logical sectors, but instead of using user data, as files do, it stores entry, special structures. Such an entry structure holds the file name, the type, file or directory, and the number of the first sector in its list. In the previous two slides, I talked about SmartFS. We have taken it from upstream and added our features on top of it. The first feature we have implemented is file system check, and its job is to validate that every single sector is same. It is executed at every boot up, and files and directories that have been identified as corrupt will be removed. It doesn't only verify the sanity of each sector, it also looks up for file loops and cross-file loops. Remember that an entry, be it file or directory, is simply a linked list of sectors and power losses or crashes could mess up the links between them. In the left diagram we have a file loop and in the right one we have a cross-file loop. The read function will never reach the end of these files and the watchdog may not even catch this. Contrary to popular belief and flash chips datasheets, some NOR flash memories do come bad from the factory. Well, some not entirely, only few pages, but having few pages unable to store data could have catastrophic results. Just imagine your heart rate or steps records being stored in such a page. The user experience will definitely be affected. The wear leveling mechanism is doing its best to ensure even wear across the flash, but at some point, some pages, sectors, blocks will have become so used that they will be unable to store data. User data integrity and device reliability are top priorities for Fitbit. Therefore, we have implemented bad blocks management. It is implemented as a hidden file, linked list of logical sectors as you can see in the blue box, where each bit within this file represents the health of a sector, or multiple sectors. The granularity is configurable. It uses CRC and read after write to detect bad blocks. Let's talk about this diagram here. The blue box represents our bad block structure, the hidden file. Just like a file, it is made up of several logical sectors linked together. The content of the first sector is shown below. In our configuration, a bit stores the health of one physical sector. If the bit is 1, its associated physical sector is good, colored with green. If the bit is 0, its associated physical sector is bad, colored with red, and it will never be allocated. As an example, to cover 8 megabytes, which is equal to 8192 physical sectors, it would require 8192 bits, 1 bit for each physical sector. We need 2 sectors to fit these bits. They don't fit into a single sector, 124 bytes, because of sector headers, which takes 10 bytes from each sector. Therefore, in this example, the structure spans across 2 sectors. The bad blocks structure has been implemented as a hidden file because of its simplicity. It reuses the code for read-write sectors. More than that, the granularity can be configured per partition such that one held bit could cover 1 kilobyte, 4 kilobytes, or 16 kilobytes. A file is a linked list of sectors with its first sector, the head of the list, being stored as an entry in its parent directory. The bad block structure has its head stored in the SmartFS signature sector, also known as the superblock. SmartFS uses a one-to-one mapping between logical and physical sectors. This information is stored in an array, in RAM. For example, for 8 megabytes of flash, it would need 16 kilobytes of RAM just for this map, assuming a sector size of 1 kilobyte. This is a lot of RAM. We've asked ourselves a question: why allocate memory for 8 megabytes if we only use 2 megabytes in normal usage and 8 megabytes during firmware update as staging area? We have identified 2 possible solutions to reduce the memory usage. The first solution would be to have 2 partitions, one of 2 megabytes and another of 6 megabytes. The latter one would be mounted only when needed at firmware update. But this solution has few disadvantages. Discontinuity, which means that we would have to split the new firmware in multiple chunks, and increased wear for the smaller partition. The smaller partition is the one which would be used 99% of the time. 2 megabytes are enough for normal usage. The other solution, which we have also implemented, is to map just enough logical sectors to cover 2 megabytes. As you can see in the diagram here, we only have 2048 logical sectors usable. The user space would see a partition of only 2 megabytes, but wear leveling would be performed across all 8 megabytes. This solution sounds really simple and it was not very difficult to implement. However, it comes with a big problem which I'll talk about immediately. The advantages of partial mapping. It can be enabled, disabled per partition. Switching between modes can be done at runtime, partial mapping 2 megabytes, full mapping 8 megabytes. Wear leveling still uses the entire 8 megabytes physical space. Only 4 kilobytes of RAM needed for the logical physical mapping. We've saved 12 kilobytes of RAM, which is 5% from the entire RAM of the tracker. The bad part is that some files created in full mapping may not be accessible from partial mapping. For example, let's assume that we are in full mapping, all logical sectors available, and we have created a new file, a.txt. We have zero control over which sectors are allocated. Therefore, our file could look something like this: logical sectors 100, 200, 3000, 400. Any logical sector larger or equal to 2048 will not be accessible once we switch to partial mapping. But what if we really need to access this file in partial mapping? The solution we have implemented to resolve this new problem is called logical defragmentation. Basically, what it does is to bring all files that must be available in partial mapping at the beginning of the flash, and by flash I mean the logical space, the area that is covered by partial mapping. It can differentiate between files that must be accessed from partial mapping and files that will be accessed only from full mapping. How it does that? The latter ones are placed under a special directory. We have this special directory whose content will be accessed only from full mapping, such as the new firmware binaries. Having this said, it replaces all the logical sectors larger or equal to 2048 with logical sectors smaller than 2048. It has two stages: exchange and cleanup. The exchange step makes sure that important files will be fully accessible from partial mapping. It sources logical sectors from the files placed under that special directory, the files that we don't need in partial mapping. This is where the exchange comes from. If there are no more exchange sectors available, free logical sectors smaller than 2048 will be used. In this diagram here we have two files. Both were created in full mapping mode. The one from the top is an important file, user settings. The one from the bottom is not, new firmware. Unfortunately, user settings, which must be available once we switch to partial mapping, has been created with logical sectors 3000, 4000 and 5000, while the new firmware file has been created with logical sectors 300, 400 and 500. After the exchange step, these two files will look like this. User settings will be stored in sectors 300, 400 and 500, perfect logical sectors for partial mapping. We do not care about which logical sectors the new firmware file will receive, because in full mapping we can access any. The second step of logical defragmentation is cleanup, and its job is to move as much unneeded data as possible out of the 0-2048 range. After we switch to partial mapping, we want to have as many free logical sectors as possible. It iterates over each file under that special directory and replaces all logical sectors smaller than 2048 with logical sectors larger or equal to 2048. Remember that with partial mapping we have freed around 12 kilobytes of RAM in normal tracker mode, 5% of the entire RAM. We have observed another place in SmartFS that could be optimized. Previously, each open file would allocate 1 kilobyte of RAM for its current sector buffer. At Fitbit, we have many open files simultaneously. As an example, if we were to have 15 open files, they would require 15 kilobytes of RAM. That is a lot of RAM. We wanted to reduce and control the peak RAM usage. This is where the sector cache comes into play. It uses a least recently used cache policy and was placed between the SmartFS and SmartMTD layers. All logical sectors, reads and writes, go through this cache. Another advantage of the sector cache is that it also addressed concurrency access to the same file. Without sector cache, the sector buffer of each open file would have to be manually invalidated. The sector cache has a fixed number of entries, cached sectors, and this number is independently configurable for each partition. All of these changes that we have made to SmartFS can be disabled, enabled through Natex's build configuration system. If we are to have a look again at all of these features, they have been implemented mostly because of two reasons: RAM usage and reliability. Lower RAM usage has been achieved through partial mapping and sector cache. Logical defragmentation was the answer to a new problem that we have added. Bad blocks management is there to make sure that trackers continue to work as intended even after years and years of daily usage. We have traded a lot of code space for RAM. Fortunately, that one was not that much of a problem. Thank you for your time, and if you have any questions, I would be more than happy to answer them.
Hello. Okay, guys. Um, Julian, are you
Yep.
here?
Yes.
Okay.
Yes.
Okay. So let's to start the questions. Mhm. I don't see many questions here, but let's wait a little bit. Maybe
Yeah.
people.
Yeah. Sure. As I've mentioned in the presentation, each features, uh, each one of the feature we have implemented for SmartFS can be disabled through kconfigs. So code space could be controlled for some devices.
Great. Okay. Mm. Just a second. Let me open the Q&A document here. Maybe it has some. Yeah. We don't have.
So I see that we have a few questions right now. So may I read them?
Let's see.
So we have, what about NAND flash? We do not use NAND flashes at Fitbit, so I cannot answer this question. We only use NOR flashes.
Okay.
In your experience,
Yeah,
yep.
the other one.
The
Yeah.
other question, in your experience, how much flash fails and how quickly? So we have run a test at one point, and we got some off-the-shelf NOR flash chip, and we have stress tested them for weeks, and we picked up few erase blocks, randomly picked, and stressed them, and they have reached a million erases, even if their vendor guaranteed them for 100,000 erases. So they lasted 10 times longer than what was mentioned in the datasheet. But we have also seen in the early prototypes, we had issues with NOR flashes because we have stumbled across some chips which had few pages unable to store data, and they caused us a lot of problems. And this was the reason we have implemented bad blocks management, even if the chances to have worn out blocks is pretty small. We want to make sure that it doesn't break the device. The user is still happy and has a great user experience.
Okay. Let's see. We have other questions here. Tend to cluster or just random across the device? They are more together, more in cluster, or they are
Yeah.
more.
They are more in clusters. Yeah.
Okay. The other question is not here, but I will ask you. Did you consider using the uh, Samsung journaling support that that Samsung included in SmartFS, or you didn't look at it?
No, we haven't considered using it.
Okay. So let's see. We have any other? Yeah. Yeah. We don't have many other questions. Also, once again, if someone he has some other question, please go to the forum and talk directly. If you want.
Yep, definitely. I will be more than happy to answer your questions.